Hello, welcome back to the stream. I'm Jared. I'm a Rubyist, entrepreneur, something. I run an agency called Super Good Software where we build Ruby on Rails-based e-commerce systems using a platform called Solidus. This year, like last year, I'm working through the advent of code puzzles. I already did day 20 earlier today, or only like half an hour ago I finished, maybe less. And I'm about to embark on day 21. Let's see how far we get. Dirac dice. What does that mean? There's not much to do as you slowly descend to the bottom of the ocean. The submarine computer challenges you to a nice game of Dirac dice. This is a game that consists of a single die, 2 pawns, and a game board with a circular track containing 10 spaces, marked 1 through 10 clockwise. Each player's starting space is chosen randomly. Your puzzle. Player 1 goes first. Players take turns moving. On each player's turn, the player rolls the die 3 times and adds up the results. Then the player moves their pawn that many times forward around the track. So if a player is on space 7 and they roll 2, 2, 1, they would move forward 5 times to spaces 8, 9, 10, 1, and finally stopping on 2. After each player moves, they increase their score by the value of the space their pawn landed on. Player's score start at 0, so first player starts on space 7 and rolls a total of 5. They would stop on space 2 and add 2 to their score for a total score of 2. The game immediately ends as a win for any player whose score reaches at least 1,000. Since the first game is a practice game, the submarine opens a compartment labeled deterministic dice, and a 100-sided die falls out. This die always rolls 1 first, and then 2, then 3, and so on up to 100, after which it starts over at 1 again. Play using this die. For example, given the starting positions 4 and 8, we go 1, 2, 3, 4, 5, 6, so on. Okay, that all makes sense to me. Since player 1 has at least 1,000 points, player 1 wins and the game ends. At this point, losing player had 745 points and the die had been rolled a total of 993 times. 745 plus 933 is 739,785. Play a practice game using the deterministic 100-sided die. The moment each player wins, what do you get if you multiply the score of the losing player by the number of times the die was rolled during the game? Okay. So we can head over to day 21 spec here. We can also day 22, day 21, part 1. We have an expected result. I'm running this with the test input, and we can grab ourselves the test input, which I assume it's just that. My puzzle input, yes. Okay. So P1 start, P2 start are going to equal the inputs strict split on new line and then map. This will give us 2 lines inside of this block, and I am going to do the laziest thing I can do and split it on spaces, take the last value and convert it to an integer. Verify that works by running their specs. In fact, let's forget to focus the spec and control what we're working on, and then that's not the right command. Bin our spec, we should have P1 start and a P2 start. All is well. Let's make these instance variables. I mean, these can be positions, really. All right. And P1 score is going to be 0 as 2 score. We'll have to implement the die, but then we can sort of come up with our logic here. We're going to go until, actually no, we'll just do this in a loop. We have sort of 2 break conditions. So who starts again? That one goes first. So player 1's move is going to be die 3 times map roll. Actually, this, I'm too clever here. Let's just data roll. And I'm going to be lazy about typing and call these POF. So, there are what, 10 spaces? 1 through 10 clockwise. So I'm going to be getting some off by 1 errors. I number them 0 through 9, and I'm just going to the inputs I get, starting positions. Annoying. All right, so we know the move. Then we do P1 position equals P1 position plus move modulo. Where's my modulo operator? 10 P1 4 plus equals P1 position plus 1. Finish that correct, right? Yeah, value of the space, there's pawn stopped on. Yeah, makes sense. If P1 score greater than or equal to 1,000, then we're going to return the answer. Then we're going to do the same thing for all of these P1s. We're going to replace P2s. Huh? Oh, that wasn't right. P1, P2. And the answer we're looking for is the losing score times the roll count. This, we're going to return P2 score times die.roll count. And for this one, we return P1 score. There's die.roll count. Now, if we run our specs, we should fail because there's no deterministic die. And we can make one, but it doesn't respond to roll. So we want to implement be bad at typing. We're going to implement roll. And then we're going to implement roll count. Cool. So that's totally wrong, but we can hopefully this is just going to be roll count. Currently, I determine this as die should return roll count. Should add 1. And it should return roll count. Hit -1 modulo 100 +1. Is that the right one? Yeah. Okay. Okay. That work? Come on, give me a first try for once. There we go. Okay. Okay, 21.1. That's relatively easy. A lot of junk just to type out, but not too bad. Now that you're warmed up, it's time to play the real game. Second compartment opens, this time labeled Dirac die. Out of it falls a single 3-sided die. As you experiment with the die, you feel a little strange. An informational brochure in the compartment explains that this is a quantum die. When you roll it, the universe splits into multiple copies. One copy for each possible outcome of the die. In this case, rolling the die always splits the universe into 3 copies, where one outcome of the roll was 1, one where it was 2, and one where it was 3. The game is played the same as before, although to prevent from getting too far out of hand, the game now ends when either player's score reaches 21. Using the same starting positions as the example above, player 1 wins in that many universes, while player 2 merely wins in that many universes. Given your starting positions, determine every possible outcome. Find the player that wins in more universes. In how many universes does that player win? Wow. Well, that's fun. That's a big number. Is there something clever we're supposed to do here? It's like 444 trillion. Not exactly iterating over that many things. Nice jasmine tea. Just a sec here. Okay, sorry, back. This is one where one of my friends said that their part 1 did not share any code with their part 2. I can see why that might be. This is very tricky. Sorry, just checking something. So like we can model this as a tree. Going to have a lot of things in it though. Okay, so this is, I think, one of those puzzles where we need to hunt down possible, hunt through the full tree looking for solutions, but we can memoize subtrees because if we see any state that we've seen before, then we know the we don't need to recompute it. We can use the value that we previously computed for. So we and since there's only like 100 possible states, sorry, 100 possible positions on the board, and only what's that? So there's 100 possible ways that the two or 100-ish ways that the two pieces can be positioned, and then there's I mean, it's still a big number, I feel like, but maybe this works. So I probably want to do something recursive. So we can keep this. Here's everything else we don't care about. Fact. Can avoid getting that just by moving this code into the solution. Okay. So we no longer care about the number of times the die has been rolled, so we don't have that state to keep track of anymore. So I think they've thrown away that. Partly why they've thrown away that mechanic. What else can we? What else do we know here? So, solution. I'm terrible at typing today. I don't have the like, it's not the keyword I usually type on excuse anymore. So we're gonna introduce a class, or sorry, a struct. Game, and so we're just gonna call it state, and it's gonna be a struct. It's gonna have one position, two position, one score, two score. And so we can create our initial state. Initial state is going to be state.new, and sorry, I'm going to use keyword init true. So that I can just copy these, make it nice and easy to read. Okay. We have an initial state. Now, does this take a block for me to like do more class stuff in here? Yes, it does. Cool. Oh, I'm not showing the code. Thank you. I've managed to not do that in so long. All right. Okay, so sorry. Luckily we haven't got too far. All we did was put in the expected result of part 2 here, and then we wrote this tiny bit of code where I modeled the state, the current state of the game, as a Ruby struct. I've got a hash where I'm going to map. We can write tiny little methods. So let's states is going to be a little hash here. So I want a wins method. Takes a state and returns P1 wins, P2 wins. It's going to do this. So if the state represents a player 1 win, then we are going to return 1, 0. Else, if the state represents a P2 win, then we're going to return 0, 1. Otherwise, so this should be returns. We'll just make them a nice little Ruby post. What are all these postfix? Conditionals. Okay, so we have our base cases. Now we want to write. We call those guard statements in Ruby, even though they're not anything syntactically special. Thank you very much, Xmessage, for pointing that out to me. Otherwise, we're going to sum up state.next states so if I have an array, here's a thing I've never tried to do in Ruby, but kind of want to do right now. A equals 0, B equals 1. Is it possible? Is it legal to do? No. I mean, that should be. P1. I'm sure there's a better way to do this, but we're just gonna we're just going to each over them. Variable naming is hard. grab our wins from our other states. Now we just need to implement P1 win, P2 win, and next states. P1 win is going to be P1 score is greater than or equal to 21. I'm so good at just teleporting around this document. That's the same thing, and then we just have to implement next thing. Oh, we don't know whose turn it is. Right. So we have an additional piece of information to track. And none of this is memoizing. That will come later. Once I get this working and realize it's too slow, because I will, because there's trillions of possibilities. Apparently. Okay, next states. So P1 turn, so that means I want to initialize it with P1 turn false. I'll need to put conditional in here. So if P1 turn false and in each of these cases, you get 3 possible rolls. I think it's going to be a map here. I'm going to map it onto just have to figure out the values for it. If it is P1 turn, oh, this should be true. So it starts on player 1's turn. If it's player 1's turn, it will not be player 1's turn next time. That makes sense. So means player 2 is not going to move or change score, but player 1 will. So let's roll. And do that. And then we need to increment the P1 score. Sorry, this is right. We need to do the -1 modulo and then we just add that. I think it's relatively simple. And then in this case, we're moving P2. P1 is not moving. P2 is. And it goes back to being P1's turn. All right, let's go run this and see how many mistakes I've made. All right, well, that's fun. Expected 444 trillion, got a struct. Well, that's unexpected, to say the least. What did I do here? Solution is I just call initial and then I don't do anything. So we're just gonna call wins initial an array. Now we should get something more exciting. Day 11. P1 score is nil. P1 score should never be nil. Oh, because my initial value. Still using those. Cool. All right. Got 3,157. That seems like too low a number. Now I missed something. What have I missed here? I mean, we're never using this. I know that. My memorization is never happening, but what the heck? So I don't think I even care about this. Exactly where I should start debugging. All right, so let's just do them and let's see if that's true. That looks like a P1 win. Yeah. Look like. What am I missing here? Let's go with this puzzle again. Each possible outcome of the die. In this case, rolling the die always splits the universe into 3 copies. One of the outcomes 1, one's 2, one's 3. The game is played on. Same as before, a lot of friend things are getting too far out of hand. Game now ends when either player's score reaches 20, at least 21. In the same starting positions above. We get. That's a lot of universes. Okay, sure. That's lots. For 3,000. What am I missing? 3 is much too small. Am I missing some kind of multiplication or something somewhere? So we should see situations. Say cities were all end states. We'd see 1, 2, 3, 4, 5, 6, 7, 8, 13, 14, 15. So this one. We're just adding them, aren't we? What are we missing here? I expected this to take way longer. So for each state, we take its next states. I'm curious. An array pairs. Zip that. Or not zip that. Transpose it. So that's actually what I want, right? Out of this. Maybe be a little more clever about it. Okay, continue to get the wrong answer. It's the same wrong answer. Why are we encountering so few possible states? This roll logic is wrong. Guess I can try taking a look at that. So, given Q1 position is 1, roll 1. We expect to be on. Not in fish again and not in pry. In position 2. But by 9, we should be in position 10. If we were to somehow roll a 10, we would be in position 1. We're in position 9. 2, we should get to position 1. Yeah, that logic all looks sound. We're not doing any manipulation here. Dang it. This all looks really clever and it just doesn't work. I'm just lost as to what I'm doing wrong. I obviously missed something about the problem. Yeah, greater than equal to 21. When 51. Yeah, it's just that's simply too low a number, isn't it? Yeah. Single 3-sided die. For each possible outcome of the die, in this case, rolling die always splits the inverse into 3 copies. 3. Huh. Like so the approach I'm taking, I look at the initial state and I ask how many of the outcomes for each possible next state from that state result in wins for each player. And then I sum those all up. And so it should recursively descend through all the possible states that we encounter. Hitting the base case where somebody has won, in which case we know that is a single win for either player. Recording it as such. I'm just lost as to why this producing such low numbers. Any ideas, chat? Am I just totally off on my approach? must have just mistaken how this problem works. I'm just lost on where my thinking has gone off. It's definitely some kind of path that involves somehow it's going to involve like tallying the number of universes that see each state, but not seeing that solution. Hmm. Isn't this working? Okay. I'm struggling this year. Doesn't look sensible. I feel like it's something core to my approach that's wrong here. But even the numbers I'm looking at are too big for me to like manually do anything here. So many ways to get to 21. just complaining to my friends that this is hard. You know, clearly it just must be an error in my thinking. Like, if I explore the whole decision tree, this is the number of possible universes, is it not? Even if some of these are like the same outcomes technically. So shouldn't I be able to just recurse and be like, oh, this is a win, or one, this one try this, one try this, one try that, etc., 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 etc. Sum them all up through their parents, set them all up here, and call it a day? Like, I'm expecting that to hit a point where I need to memorize it, not that I'm not recomputing full subtrees that I've already computed, that I've already encountered. Oops. To do it for 1,000, it should be slow. Shouldn't work. Yeah. Yeah. Okay, that's exactly as we expected all to be. I'm gonna need some help on this one, I think. Well, let's go see what other people's solutions look like. We're looking for admin code. didn't type, but I didn't put the slash r in. Okay. Okay. So let's see. I mean, a list solution is going to be super helpful. Makes effector of all possible states, goes through in 2 passes. In first pass, basically generates a graph of all possible state transitions along with their weights. In the second pass, it calculates the total number of paths to each state. It needs 2 passes because the second pass I can't determine if I can move from a state unless I know I've covered all the possible ways to get to it. It takes about 30 milliseconds. Okay, interesting. Now, like, yeah, I thought this was a dynamic programming problem. And that's how I'm tackling it, I think. But obviously, I've just, like, yeah, simpler subproblems in a recursive manner. That's clever. What? P1 score, P1 position, P2 score, P2 position, got second part running down 30 milliseconds. Yeah. Okay. I can read NIM or slang. I mean, I like this idea. I mean, we can do. I like this. I like this approach. I don't know. Like mine looks like it should be turning into the dynamic programming one, and except I'm not doing the like. I'm not actually storing my results, but it doesn't work. So maybe I'll come back to that at some point. K21 part 2, but it doesn't. My dynamic programming don't work. And yeah, I know this isn't quite dynamic because this is just a recursive solution currently, but whatever. Okay, I mean, we can still we can still do this. We can do it as a loop, and it'll be fun. Everything will be cool. So until so let's see. States. It's going to be a hash. It's going to be a hash where the default values are zeros, and until states.keys.all done. We're going to do a loop. We just need to add a done method up here where P1 score, oh, so we do P1 win or P2 win. So then we do states.reject done each do this is a hash, so we actually have to be a little more clever there. So we're gonna have a key and a value, state and account. And in here, we want to reject them if the state is done. And then we have state, account inside this block. How does this work? So we're counting how many times we've seen each state as we encounter it. Tricky. So we come on, brain. Two hashes? Just trying to think through this. I liked what I was hearing, but I'm just trying to understand how to implement that. The number of possibilities for different not yet winning position score states reachable by each player for that turn. While accumulating the total number of possibilities for each player winning. Gosh, this is horrifying. sorry. It's not really horrifying. Simulate each possible reality and maintain counts just like the other puzzles. Damn, I'm having trouble wrapping my head around this. Okay, try something. So if we iterate through the turns until we have no so I'm gonna, so suppose final states, done states, consistent, and so states is going to be that, I think. And we'll go states dot plot. So I want to produce new. This isn't going to work. New states equals hash. new states. This thing's janked, but for each state, count, we want to get the possible next states. State next states each do, and this will be a next state. So if next state dot done, then we want to increment done states by count, because that's how many states we've accumulated that ended in that done state. Otherwise, we want to add and so this will need to be another default 0 hash. This will also be equals 0. Set that. It's consistent. And we'll just break if new states empty. And binding on the other side. Oh, not decommitted. That's a little premature. New states. Sorry, this should be states empty. Get there the other side, so we should have done states, which is a lot of things, but at done states thing, it has 1500 values in it. Keys.sum, values.sum event. No. This looks like the number of universes that I select K B K dot B1 win some A B B. No. So this produces the same numbers I had before, suggests to me I must not understand something right. So I've now done a totally different approach that also makes sense to me. And I'm always unless there's something really core to my state logic here. That I've done wrong. This is tough. The fact that I've produced the same wrong result 2 different ways is alarming at best. Oh, it's 3 times. I'm not rolling 3 times. Oh, should have just looked back at it. Okay, well, there we go. That's fine. That's easy. Fixable. Just makes me sad. I should have trusted my gut and been like, logically, this all makes sense. Everything should be working correctly. I must have an error in my thinking. I was thinking of the tree structure, not the number of rolls. But I get for sharing no code between the 2 versions. I'm sure I would have identified that. Those numbers are still too low. They're in the billions. Oh no, those are in the millions. But we do need to treat 3, 2, 1 differently from 1, 2, 3. Oh, and I haven't done P2. Okay. Still need more. Okay. Okay, so that's gonna be the right answer. So it's now, that's the number of times 1 wins, that's the number of times 2 wins. You want the maximum of those 2 values. Brutal. Okay. Pick number. Okay, well. Thanks. Brutal having to just being bad at remembering what the actual problem I'm working on is. That's tough. Is what it is though. Still kind of a fun problem. I'm just removing that. Got some slow specs in my spec suite. Thanks everyone for coming out and watching me forget to roll the dice 3 times for like half an hour there, whatever that ended up being. As far as I know, I'm back again tomorrow night, or maybe even tonight. We'll see. I might come back for tonight's problem. We'll see. We'll see what my energy level's like. But that was fun. See you later.